Hi, everyone. My name is indeed Vincent, and I'm leading the scene representation group at MIT. And our goal is to build spatial artificial intelligence, or in other words, we want to basically teach artificial intelligence to see the 3D world in the same way that you see the 3D world. And what do I mean by that? Maybe the goal really is to build artificial intelligence that learns these things self-supervised. So we want to basically build as little upfront information into the architectures that we have as possible. And let me motivate that a little bit. And if you would, I would ask you for a little interactive experiment. So I'd like you to look around for a moment around you. Maybe look at a bottle that you have with you, look at the backrest of the chair in front of you, or maybe a notebook that is lying next to you. And I'd ask you to close your eyes and to reach for that object that you just looked at. Maybe try to not reach for your seat neighbor. Okay, and like maybe pick it up if it's pick-upable, or just like, okay, that's it, great. So I assume most of you succeeded at grasping for the object that you looked at, and you were probably not surprised by the fact that you were able to do that. But I'd like you to wait for a moment and understand how incredibly impressive it is that you can do that. And why is that? Right? What you have in your head is two eyes, and your two eyes constantly see 2D video of the world around you, right? They just observe video, that's it. And from this 2D video, your brain has learned to constantly reconstruct a 3D representation of the world around you. And what I mean by that is that there's some kind of representation in your brain that encodes all of this information about the objects around you. It tells you how heavy an object would be, how you would have to approach it to grasp it, how it would feel to the touch, would it be soft, would it be hard, how much force would you have to bring up to grasp it, all of these things, right? And you learn all of these things not through some huge labeled data set of like objects and how heavy they are. You learn that by just being a human, right? Like as a little baby, you like grasp for stuff, you bite it, you throw it, and that's how you learn about how the world works. And that's our objective as well, right? So we basically want to build AI that without supervision, just from interacting with the world, or even maybe passively just from looking at video, although that somehow limits what you can learn about the world, just from looking at video like that, we would like AI to, for instance, figure out, oh, you know, these are the kinds of objects that exist in the world. This is the geometry of the 3D world. This is what happens if I grasp for an object, and so on and so forth. So the first question you might ask is, what is the data? And it turns out the data that we're going to use is exactly that data. It's really just video. That's what we want to use as our data set. And the key signal that we will be looking for is the signal of predicting the future. So basically, the hypothesis is, right, that what you're constantly doing is you basically constantly predict what will happen next. What will happen next if I move my head? How does the image on my retina change? What will happen next if I reach for an object and I touch it, and so on and so forth. And we want to use that very same signal to train our artificial intelligence. So imagine you give it a set of frames of a video, and then you ask it, OK, what will happen next? Tell me what will happen next. And in that way, you can basically train the AI to just predict what will happen next and understand much of the world. What can you understand from that objective? We can think for a moment about what is the structure of video. If you look at this unfortunate video here, basically, every video can be explained by approximately 3 factors. One is the 3D geometry and appearance of the underlying scene. One is the camera motion. So how does the camera move throughout the 3D scene? And then the final one is how is the scene itself moving? So in this case, the hands are moving, the plates are moving, and so on. So now imagine if you trained an artificial intelligence that could look at a subset of these frames and then predict what would happen next. These are the things that your artificial intelligence would have to discover by itself in order to tell you what would happen next. Does that make sense? Fantastic, good. OK, so recently we've made, and when I say recently, I literally mean in the last 4 years, we've made fantastic progress on one of these axes, which is the axis of 3D reconstruction from video. You might have seen results like this one. So these are both 3D scenes that are reconstructed just from images. So this is just a set of images. From the set of images, we can reconstruct the 3D scene, and then we can render it from any arbitrary perspective. And if you think about how that relates to our motivation, right, think about that this is basically a video that is generated by reconstructing the 3D geometry and appearance of the world. And afterwards, you can move the camera, and that generates a video, right? So this is an example of how we can build algorithms that recover structure just from video. So one problem that also Luca touched upon is that so far, 3D reconstructions don't really have any understanding of the underlying scene. They're just really, this is a representation. It's kind of a dumb representation. Just in the same way that an image doesn't understand what the content of an image is, this representation doesn't have any understanding that this is a representation of a playground. So how can we fix this? We have trained lots of, recently we've trained lots of neural network algorithms that succeed at so-called like open set semantic segmentation or open set scene understanding. So here's a model called Dino V2 that was trained by Meta. And if you look at this video, you can basically tell that on the bottom right, you can see the output of this algorithm. You can see that the semantic parts of the dog always get the same color, right? So basically, this algorithm has discovered by itself how to semantically segment the scene. This algorithm has seen 0 labels. Like no human has ever labeled a dog for this algorithm to figure this out, nor has any human ever went in and labeled like parts of an image or something like this. So this is completely what we call self-supervised. So now it turns out we can basically take these semantic segmentation features that we have learned in a self-supervised way, and we can basically, instead of just reconstructing the RGB color of our 3D scene, we can train our model to also reconstruct the semantic features of the 3D scene. And I'm gonna skip over the technical detail here, but what you get from that is quite cool. So here you can see one of these 3D reconstructions, right? So this is just what we call a radiance field. And then this is the semantic features that we lifted into the 3D scene from these 2D images. We basically lifted the semantic features into the 3D scene. And now, basically, what we have done is we have endowed this 3D representation with semantic understanding without ever labeling a single data point. No human has labeled anything ever for this model to work, right? And now what we can do at test time is we can go in and we can, for instance, use this for editing of the 3D scene, right? So you can go in and you can say, okay, you can select a point on the flower and say segment the flower. And then you maybe saw it earlier, you can segment out the flower, you can change the color of the flower. If you have a vision language model or a model that gives you features that are aligned with language, then you can also use language to segment out the scene. So for instance, you can reconstruct this 3D scene just from images. Then you can take a language query like flower, then it segments out the 3D scene, and then you can edit that part of the 3D scene just from images. Okay, so this is pretty cool. So here's more examples how you can use this for 3D semantic segmentation. But again, note that there's no training set that was labeled by humans here. So you didn't require any labels for like the chair or for the TV or anything like that. And this is, by the way, a crucial point, because this is getting, at the end of the day, right, we want to attain the level of generality that you have. You don't need to be told, you don't need to collect lots of labeled data to be able to identify and grasp objects. Cool, so this has, so colleagues of mine here at MIT, Philip Isola's group, have used this kind of representation in robotics. So here you can see an example where we can scan a 3D scene. Then we can basically distill these features into that 3D scene just the way that I just showed you. And then afterwards, you can solve exactly the problem that we set out for without ever telling this robot anything about what a Baymax is. In fact, I don't know what Baymax is. Apparently, it's this character. The robot can then go and pick up this object and then put it into a box, right? And now imagine what that allows you to do, for instance, for automation for packaging. You don't need to collect data sets anymore. You can just put this robot on your manufacturing line, and without ever labeling the objects that it's going to see later on, it can just perform the task. So this paper is called Decomposing Nerve for Editing via Feature Field Distillation and was written by Kobayashi et al. In collaboration with me. Okay, so this is really cool, and this is very practical. So people, I'm now collaborating with Philip, who wrote the paper with the robot, and we're pushing this way further than what I just showed you. It's very exciting. But there's one huge limitation about the stuff that I just showed you, which is that it's not really all that scalable. So the stuff that I just showed you, similarly to some of the things we saw earlier, still requires that you have lots of images of some 3D scene. What that means is, right, like if you want to pick up an object, maybe you need to see this object from every possible angle, because that's what you apparently need to reconstruct the geometry of the object, such that then the robot can grasp it. But of course, that's not how you work, right? In fact, when you looked around you earlier, right, you probably, if you reached for an object, you saw that object from exactly one angle with your two eyes, right? Like I can put this bottle here, and I don't need to go around the table and look at every possible angle to just be able to go and pick up the bottle. This is something that comes natural to us humans. And that's because we have learned what the 3D geometry of objects is, and we have learned to reconstruct that from a single image or from very few image observations. And this is the second line of thought that I want to talk about. So the way that these neural networks work is actually that we take a small set of input images, like maybe one or two, or like a short video. And from this small set of images, we actually train a neural network to reconstruct the 3D scene in a single forward pass. So it basically just looks at these images and then spits out the 3D representation. And it only needs very few images. And again, you might ask, okay, great, but if we want to train a neural network, do we need a huge data set to do that? And the answer is no. Because in just the same way as earlier I showed you, you can reconstruct 3D scenes just from images, we can actually also train this neural network just from images. We don't need any other data than video to train these neural networks. Okay, so what that allows us to do, so what that allows us to do is we can take a single image and reconstruct the 3D scene. But there's a little bit of subtlety that I want to talk about, which is that, let's say I ask you to do this. Let's say I ask you to look at this fire hydrant here, and I ask you to imagine what this fire hydrant looks like from the other angle, like from the back, for instance, right? You can easily do this, right? You can look at this thing and you can imagine, okay, maybe it looks like that, maybe it looks like that, maybe it looks like that, no problem. But you notice that you have uncertainty, right? You don't actually know exactly what it looks like, because you don't know exactly, for instance, what the texture is, or you don't know what the exact geometry at the backside is. And if we train our neural networks to just naively reconstruct the 3D scene, then that does work. What we have to train our neural networks is we have to train them to be aware of this uncertainty. So in fact, all of these reconstructions here are outputs from our neural network. And what our neural network allows you to do is it allows you to sample from the distribution of all 3D scenes that is consistent with your observation. So why is that important? Imagine you want to pick up a mug, for instance, and you have a robot that wants to pick up a mug, and it wants to pick it up by its handle, but the handle isn't visible because the mug is facing away from you, right? The handle of the mug is facing away from you. What you need to know is you need to be able to say, okay, I know that the mug has a handle, but I don't know where. You won't need to be able to represent that uncertainty to then be able to say, okay, I'm going to look where the handle is. And that's basically what this algorithm allows you to do. If you don't do this kind of uncertainty modeling, this is what you get. Like from a single image, you try to just reconstruct the 3D scene naively. You just get a blurry mess because your algorithm has to collapse all possible reconstructions of the scene into a single one, which basically means it's going to get blurry, and then it's just garbage. And compare this to the reconstruction of our algorithm, which basically gives you, from a single image, a 3D representation that is quite good. Of course, this is still not quite the level of photorealism we're looking for, but it's getting there. And the cool thing is that this really doesn't only work for these kinds of objects. This also works for room scale scenes. So here's a single image of a kitchen. And from the single image of a kitchen, the neural network has learned to reconstruct all possible, not all possible, but many possible kitchens that are consistent with the single image. So here, each of these scenes that you can see is the output of our neural network. And this is actually a 3D scene, like there's a point cloud for each of those. And from this single image, we can then sample from several possible kitchens consistent with that single image. Does that make sense? And this, for instance, you can imagine is important if you want to have a household robot. And you tell the household robot, I don't know, go to the kitchen. But maybe the robot hasn't been to the kitchen yet. And it needs to be able to say, like, okay, behind which door is the kitchen, right? It can be like, it could be behind this door, it could be behind that door. Okay, I'm not going to talk too much about the technical details here, but although they are very exciting, I'll just leave you with one connection that you might know. All of you have probably seen these image generative models, right? So these models that you can give them a text query, and then from the text query, they allow you to sample an image that is like super high quality, right? So like, for instance, these images are images generated by neural networks. And the algorithm that I just showed you is a similar type of algorithm. It's an algorithm that allows you to, given an image, sample from the distribution of 3D scenes. The tricky problem that we have to solve, however, is that if you try to build a generative model of images, that's easy because we have lots of images around, right? With 3D scenes, we don't have any 3D scenes around. We don't have a huge data set of ground truth 3D scenes. So how can you build these models are called diffusion models. How can you build a diffusion model that learns to sample from the distribution of 3D scenes, even though you only have access to images? I'm going to skip over that because I think we're out of time. Although the basic idea that you can imagine is the way it works. You give the algorithm a single image, then you tell it to reconstruct the 3D scene. Then you give the algorithm another image, and you say, I have uncertainty about this other image. I don't know what the scene looks like from this angle. And then you basically say, okay, you add noise to that image and say, consider under this noise pattern, how could the scene turn out to be? And then you do it again and again. And that's basically how you can build a diffusion model that samples 3D scene, even though it just sees images. We don't have enough time to look at that, unfortunately. Let's skip over that. So here's a comparison with neural network baselines that came up before. So you can see from a single input image, this is an algorithm called PixelNerve that is not aware of the uncertainty, and you can see that it really doesn't do a very good job at it. This is concurrent work, in fact, that came out with our paper called sparse fusion, and this is the output of our algorithm. And just to give you an idea of another idea of this uncertainty estimates. So here's a single image. And on the right, you can basically see for every pixel of the image, how much does that pixel change every time we sample. And you can see that every part of the 3D scene that wasn't observed in the input image changes a lot, while every part of the 3D scene that was observed in the input image stays constant, right? And that makes sense because for those parts, we don't have uncertainty. For every other part, we have lots of uncertainty. One tricky question is, like, if you look at this oven here, you can see that the oven changes a little bit, even though the oven was seen in the input image. Usually, I would ask this as an audience question, but can you imagine why there is uncertainty in the 3D reconstruction of this oven, even though it's visible in the input image? And the reason is that given a single image, you're actually not entirely sure how big the oven is, right? It could be like a little bigger and further away. It could be a little closer and smaller. And this is actually also something that is captured by this uncertainty estimate. OK, this is work by our postdoc Ayush here at MIT. So there's, mostly I talked about these two different angles, right, which is like how can we endow 3D representations with semantic information without ever labeling any data, and how can we train neural networks to reconstruct 3D scenes just from a single image. But of course, there's lots of exciting work that we didn't have time to talk about. There's lots of applications in robotics, as you might imagine. There's lots of applications in computer graphics for 3D editing and for tooling for visual artists. And then there's also a new interesting line of work that we're exploring on a new approach to like this classic problem of estimating the camera pose from video, which Luca is actually also an expert on. So key takeaways, and then I'm going to wrap up. It turns out that we are really nearing a breakthrough in 3D understanding from images. And this is fueled by progress in self-supervised vision and in this algorithm called differentiable rendering. And what I mean by that is, and this is a prediction. Of course, predictions are noisy. I would guess that in 2 years from now, you would literally be able to take your phone camera and place it somewhere in the scene. And from that video stream, you will be able to get a real-time 3D reconstruction of whatever is happening in the 3D scene. And when I say 3D reconstruction, I don't mean depth. I mean literally, you can move the camera and look at it from a new angle. And you can imagine how incredibly useful that would be for robotics, right? Imagine the videos that we saw at the outset of like these videos of someone manipulating objects in a kitchen. Imagine that for each of these videos, we can now get a 3D reconstruction that tells you the geometry of the scene, how everything is moving in the scene, and so on and so forth. This is going to be huge. Of course, this has huge applications in graphics, robotics, augmented reality. And another thing that I'm personally very excited about, some problems we can always solve by in engineering and by smart engineering, and that's great. But beyond just solving engineering problems, there's a question of intelligence, right? There's a question of like, how can we build algorithms that learn these things by themselves? And vision is very exciting for that, because for vision, we know a lot about the geometry of the problem. We know how the 3D world works. We know how cameras work. We know lots of other things. So when we train these models on vision problems, we have a much better understanding than if we train these models on language. Because for language, we have no idea about how does the geometry of language look. But we know very well what the geometry of vision looks like. And this actually offers a huge potential for exploring new neural network architectures that tell you about, that are interpretable and that have guarantees for discovering structure from data. This is my research group at MIT. We just started a year ago. It's very exciting. And yeah, please come talk to me if you want to hear more. Thank you very much.
We have time for questions, if there are any.
Hello. So you're creating a 3D reconstruction, and you're using the uncertainty as like part of it. Are you able to kind of create like a heat map of where the uncertainty is, so you can like know where you're uncertain in this reconstruction?
Yeah, that's a fantastic question. So to repeat the question is it easy to, like, for instance, given a single image, then say upfront, like, what parts of the 3D scene are we uncertain about? The algorithm that I just showed you does not give you a simple way of estimating that other than sampling. Like, you can sample several times and you can just estimate the variance empirically. But there are ways in which you could build this algorithm such that you would get these uncertainty estimates upfront. But this algorithm doesn't do that. And if you're interested in that literature, there's literature on how to build diffusion. This is a kind of diffusion model, is like how can you build diffusion models to give you these uncertainty estimates upfront. Yeah.
Thank you.
Thank you.
Any more questions? I have a question. I was just curious, like how we would think about. So you talked about spatial prediction, but prediction across time. You showed the plate going down and breaking. How would you? What would you need, like in terms of data sets or something?
Yeah, this is a really, really fantastic question. So the question is like, how could we approach this problem of dynamic 3D reconstruction? And I think one way to think about this question is that this problem of reconstructing the 3D scene from a video stream is a very old problem, and it's called structure from motion. And structure from motion works reasonably well. Like SLAM and structure from motion, if you have lots of sensors and you are basically allowed to build the platform yourself, is like relatively tractable, right? Although there are still lots of limitations. But the problem of reconstructing dynamic 3D scenes, that problem has evaded computer science for the longest time. And in fact, this is a well-known thing about like SLAM and structure from motion. These algorithms, they just fail catastrophically if there's stuff in the scene that is moving. Even though, of course, as I'm pacing along on the stage, you have exactly zero problem to reconstruct the 3D scene that contains me in the 3D scene, right? And I think, to me, this is exactly one of the motivations for why we need an alternative approach to this 3D reconstruction from video problem. Because the classic approaches have taken us pretty far in the static reconstruction case, but in the dynamic 3D reconstruction case, it turns out that you just need like learned priors. You need to learn something about the world in order to be able to reconstruct scenes where stuff is moving. And for that, basically, we can talk about it later. But the way you can think about it is what you end up doing is you train neural networks that look at video. And from video, they basically predict how every point in the 3D scene is moving over time. And then you are able to connect that back to the image. And then you're able, again, to train this just from video. So basically, give the neural network some frames of the video, and then you ask it, what does the next frame look like in terms of the 3D geometry and appearance, and in terms of the motion relative to the previous frame. And then you can close the loop and train again, just given video. Does that answer the question? OK, cool. But no one has done this yet, but we will soon. So
a bit related to the other questions, I was wondering, so if I understand correctly, these models basically create a bunch of guesses, and they're each individually high definition guesses. They just vary across them. Are you able to output or extract semantic information about like the overall like loose nature of some part of your generated scene? Like, I expect there to be some kind, like your example of the handle, like in this area, I expect there to be a handle, things like that.
Again, fantastic question. So let me repeat the question. The question is, OK, we have this neural network. Apparently, the neural network gives you a bunch of guesses of what the 3D scene looks like given the single image. It seems intuitive that we should be able to extract semantic information from that. And let me just back that up. Like, why would you expect that the neural network understands the scene other than just reconstructing the scene? Obviously, in order to be able to tell me what the back of this object looks like, you need to understand something about the object. You need to understand that this object is approximately rectangular. In other words, right, if you look at lots of 3D scenes, and for every possible 3D scene, you are able to give me a good guess of what it looks like from a different angle, given a single image, that tells you that you have learned a lot about the world that allows you to reconstruct from a single image. And the short answer to the question is yes. If you look at this model, and this is something that we're currently exploring, indeed, the features that this neural network learns are heavily correlated with what you would call semantic information about the scene. And in fact, to a degree, this is the motivation for this whole line of work. The motivation is, at the end of the day, we will just train this on video. And for instance, if you're able to predict what happens next in a video, you need to understand a lot about the underlying world in order to make these predictions. And then we would expect that we can use these features for downstream tasks. Great question.
Thank you.
So this is just a fun question. How would you apply your model to the slide from one of the previous talks, which had the van with the convertible drawn on it?
The van with the convertible.
So there's one with there's a van with an image of a convertible that had been pasted on it. So it's a little hard to tell which was figure and background over there. I'm just wondering how that would work, because that's basically a 2D image masquerading as 3D. I mean, I guess if you didn't see it, yeah.
Oh yeah, I think I missed it indeed. But like, basically, what would you expect, right? What you would expect is if you have an image like that, where it could either be like an image like painted, for instance, of an object, or it could be the object itself. What you would expect is that if you have seen examples of this in your training set, right? What would the examples in your training set look like? It would look like, okay, you have one frame where it looks like a 3D object, but then the camera moves and it reveals actually it was just a painting. You've seen lots of these, right? So what you would expect to happen is if these are in your training set, then this becomes part of your uncertainty estimate. So every time you sample, sometimes you would get a sample of the 3D scene, which is just a picture, and sometimes you would get a sample from the 3D scene, which is actually a 3D scene. And what that just means is just in the same way as you are uncertain, if I give you a picture of a scene, right? You could be like, yeah, it could be a picture of a picture, right? Yeah, you would expect that the neural network would give you the same uncertainty estimate. But in reality, this is a function of the training set. And in your training set, of course, you would probably not see too many examples like that. So you would guess that, like, this is a relatively small amount of probability mass that falls onto this like degenerate case of like you just have videos of like pictures. Great question.
Could I ask a quick follow-up about that? Does this model have like temporal information gathering capabilities? Like in that case, as it sees more of the scene move, it realizes, oh, it's a painting, it's not an object, or not currently?
So currently, this model unfortunately is not able to reconstruct dynamic scenes. In fact, the progress on reconstructing dynamic scenes has been very embarrassing for the past 50 years. And I say that as part of the community. Like, our community has not been doing a good job at this. Like, dynamic 3D reconstruction is an unsolved problem. It just doesn't work in reality, right? But the only thing that is, you can think about it like this, the only part that is dynamic in these scenes is the camera itself. So the scene is perfectly static, but the camera is moving. And that is the information that allows you already to disentangle the picture of an object from the object itself. But this model right now is not able to take one of the videos that I showed you in the beginning and then, tell you what is the probability that like the hand would move like that in the next moment.